So welcome to the second half of our press briefing here today. This is very exciting. We have the first observations by Webb of Mars. So I'm delighted to welcome the team that were behind those observations here today at the Europlanet Science Congress 2022 here in Granada in Spain. We have a panel including Jerónimo Villanueva of NASA Goddard. We have Anne-Karin van der of the Royal Institute of Belgian Aeronomy. We have
Giuliano,
sorry, and we have Sarah Fabji as well, both from NASA Goddard. So delighted to have you here, and take away, Jerónimo.
Thank you. Yeah, so this is very exciting. So yeah, we have a good group. I just want to say I'm Jerónimo from NASA Goddard, and I will be telling more about this, all of us. So
yes, so Anne-Karin van der from the Belgian Institute for Space Aeronomy, and I'm mostly dealing with the coordination with other Martian assets.
As I said, I'm Giuliano Liuzzi, former from NASA Goddard, now at the University of Basilicata in Italy, and I explore the data in terms of the spectroscopy and data analysis.
I'm Sarah Faggi from NASA Goddard, and I've been working on the data reduction of the Webb images and spectra.
Yeah, so the main thing is that tell a little bit about why it's so important for us to do research. We know a lot about Mars now. We have orbiters around Mars, but why Webb is so important for us? And I'm going to give you a little talk, but before we go into that, the main thing about Webb is that it can map the whole planet instantaneously. So you get these higher spatial resolutions. You have these incredible sensitivities in the infrared. So for us, it's new science we can deliver for this new view that we have with James Webb. Of course, the challenge is, as we have in the title here, that is so bright and moves so fast that it has put some challenges on how we take the data and how we measure the data. So let's go back, let's go quickly a little bit about what is Webb able to do. So this is how Webb typically can do things. This is the Sun, Earth, and where James Webb is located. Webb can only look in those blue and red regions. This is what we call field of regard. And Mars is because it moves so fast around the Sun, and with the difference of every 2 years, there are only windows. And the window that happened for James Webb started on the 16th of August. So yeah, it just happened a few weeks ago. And right into the thing, the James Webb team got quickly to try to set all up. And then on the 5th of September, we took data for James Webb. So we have a group called Guaranteed Time Observations. We've been working on this observation for 10 years, actually, all of us. And this is something coordinated by a whole solar system, led by Heidi Hammett. She's the big lead about this. And then we have been tasked with different objects. And we are the Mars team. So what do we get? Let's go quickly to the images so you get a flavor of what are things we're getting here. So these are the first images that we took of James Webb with the filter with an instrument called NIRCam. So the thing, Mars is so bright that it has been a challenge how to see it, but we can see this incredible resolution. We have the diffraction limit of a space telescope in the infrared, which is, for us, is fantastic, and we can see the whole planet. So what are we seeing here? On the left, you can see a simulation how Mars is there. The blue square, the more smaller one, is what we use for the smaller sampling of high resolution, on the surface of Mars. And you can see the more brownish color image. What you see there, you're seeing the dust properties, you're seeing the surface of Mars, and you can see instantaneous phenomena. These are very short exposures, so you can see things which you don't have to do the slicing that you typically do with orbiters. You can actually see very high resolution from Webb at this wavelength. And the other cool thing is the other one in the bottom, which is the 4.3 microns. And what is it telling you? This is all telling you about the thermal emission of the surface. And again, typically when we measure Mars, we do this slicing. We have these different ways that we can measure now. You can see the polar area, which is colder and it's less flux. You can see what we call a terminator, which is a transition between daytime and nighttime. You can see it's getting colder. And one of the things, you see this bright thing, that is because it's very hot on Mars, and this is the brightest area of Mars. It's actually at the border of saturation of the instrument there. But one of the neat things, you can see this dark patch there, and that is a basin on Mars. And we were not expecting that, I must say. This is the hottest point on Mars at this time. This is 2 p.m. on Mars, so we were expecting something very bright, but it got darker. So we're wondering what is going on there. And it's because Veles Basin is the deepest point on Mars, and the molecules in the atmosphere are hiding some of the flux. And this is a bit technical, but I will show you what I mean by this. So here you can see in these two plots, if you look at the one on the left, those two color traces, the blue and the orange, are how a spectrum of Mars looks like if you look at for James Webb. And that green trace there indicates the filter that we're using. It's called the 4.3 filter, James Webb. So we're looking at the flux that goes only through that green element there. As you go where, if you look at the two, are very similar, but they're slightly different, the two traces, the orange and the blue. And that is because the surface pressure of Mars will hide some of the flux. If you actually zoom onto that, you multiply by that, you can see the flux is on the 10 millibar, which is a much deeper atmosphere to the nearby areas, is much different. So you lose like 20-30% flux, and that explains that big depression in flux that we saw. So you actually not only learn about the thermal properties, but you also learn about the atmosphere by looking at those NIRCam images. But I think what got us more excited, it was cool, was the spectrum of Mars. And so this is the things you can see. We actually use all the NIRSpec gradings of NIRSpec. And so this is a collage of all the gradings taken at different parts of the planet. And you can see this huge amount of lines. And this is, doesn't show all the power. And this is it's just a snapshot. These are very high resolution spectra, which is the figure doesn't show all those things. But you can see the signatures of carbon dioxide that we know is there. We also see carbon monoxide. We see water signatures. And you see a lot of other morphologies in that spectrum. So there's a lot for us to interpret. And this is where we have all this team of people, many other people also in the team, who will help us to reveal all the properties. I mean, there's a lot of signatures we can go deeper. We can zoom in these areas. The sensitivity that we expect, these are very short integration. James Webb is so sensitive that the sensitivity is remarkable. So one of the things, for example, we want to do is look for methane, and I will tell you a bit more about that. And just to tell you what are the instruments that we can do stuff, just to remind you what are the instruments that on board James Webb and we can use for things like Mars. So the upper part indicates what the instruments that we can use for imaging. And you have NIRCam, MIRI, and NIRIS are the three instruments that we can use for imaging. Mars is so bright that we cannot do MIRI, and we can mostly do NIRCam, and we only can do the two filters that I show you for NIRCam. That's why we emphasize on those. Those are the filters that we can use for do imaging on Mars. Beauty, because you get those very high resolution and also the thermal elements. And then the bottom panel, you can see the instrument that we can do spectroscopy. And I have to say, most of us are spectroscopes, so we are a little biased about that. And we can do a lot of great science with the instruments. And again, MIDI saturates because Mars is super bright in the infrared and it's super close. But NIRSpec is our main thing. This is what I showed you before. And the other instrument also saturate for spectroscopy. So we have used all the modes effectively available for us from James Webb now. The data is now effectively public for everybody to work with. We have done some pre-analysis and we are working now going deeper. We are improving the calibration to go deeper and to answer more complicated questions. And I'm going to tell you a little bit about what we are actually pursuing after this. Just to remind you, and this is possibly complex, but just to show you, these are simulations of what you expect Mars to be bright. This is colors, more reddy, it's higher colors. And you can see some white shading there. That white shading indicates James Webb will saturate. And there are 5 globes there. There are different wavelengths. They go from 0.75, 1.27, 1.8, all the way to the 3.67. So what we always we look at wavelengths that we don't saturate with the instrument, and we can do spectroscopy, especially on the 3.0 and 3.67. There are a lot of spectral areas on the planet that we can do a lot of spectroscopy. And why do we care about spectroscopy at those wavelengths? So there are many things we can do, but there are many things that we care a lot is this. For example, one of the things we can do is we can look for water on Mars that we know is there. We can map it from ground, but we can also map very sensitively heavy water, dehydrated water. And that tells us about the past of water, how much water was lost in the past. Typically, you can do ground-based telescopes, but they are very noisy because we have our own atmosphere, and also we have what we call tellurics, they absorb the light. So it becomes difficult. If you use orbiters, they tend to be slicing that, and it takes maybe 1 month, 2 months to produce a map like we show. So in this case, we get an instantaneous view of Mars, which is a novel aspect of this. And you can see the lines are going to be beautiful. So this is what we are working on right now. This is a simulation. We want to go to the data, and we are working to try to get this out and then pull out those signatures out of the spectrum and map it on the planet. And just to show you just to summarize what I was trying to say, so when you look at the D over H, which is the isotopic ratios of the planet, we know that the value, so the more to the left, you can see this, we saw the D over H enriched in the atmosphere. That happens because water has been lost over billions of years and the heavy form has been enriched. So if there is a release of new water from the subsurface, or you're looking for new water in the atmosphere, you may be able to look at that by the DO bridge. So the DO bridge not only tells you how much water was in the past by looking at the blue at the left side of the panel, but also you can look for new water reservoirs on Mars. That's why it's very powerful, and it's very difficult to do from ground because of the tellurics. So now we have a very powerful technique to do it, and that's why we're trying to tease the data as much as possible to go there. And this is just to sample what I was saying. One of the things we did with ground-based, it was just a snapshot that we did from ground-based. You can go back in time and you can use that information to infer how much water did in the past. And so the idea is to use Webb complementary with the previous work, complementary with the orbital data or rover data, and use all that together to get a better idea about the past of Mars. And this is, it tells how water gets lost over time. And the final topic that I wanted to discuss here today was about organics. So we want to look for organics on Mars. And there's been a lot of debate about, for some methane on Mars, some initial ground-based observations that I was actually involved. Then there was this claim that was maybe not right. Then there was the orbital, there was a Curiosity rover making detections and sporadic releases. We've been working a lot on doing TGO, trace gas orbiter measurements, and we don't see it. But the big conundrum has been is that the rover is on the surface and the occultation data is only sampling all the way up to 10 kilometers. So there's a gap between 0 and 10 kilometers. If you do it from ground, you have all the methane in our own atmosphere to hide the signature, so it becomes very complicated. Now we have James Webb. We don't have tellurics, we have extremely sensitivities, and we can see the full column all the way to the surface where the rover is. So we provide a new way to pinpoint, to solve this conundrum. That's what is one of our main targets right now. So just to show you, it's not going to be an easy measurement. This red thing you see there, this is 50 ppb, which is now on the high end of what could be methane on Mars. And you can see it's going to make a drop around 4% on flux. So it's a very small signature. So that's why we're working heavily on the data, trying to improve the sensitivity so we can make sure that we can achieve that sensitivity that we are expect to get, but we want to go deeper to get a very sensitive measurement of methane. And just to remind you why methane is relevant. So if methane is on Mars, it could be produced by these processes effectively. You have a comet hitting Mars, which could be pretty cool. You could also have, for example, underneath the surface of Mars, you could have, for example, geology, acting very low temperature geology producing that gas. And that has been so interesting because it will imply that something is happening today on Mars. So something hit Mars very recently, within the last 300 years, or maybe there's a geological activity. And of course, the most interesting thing is that, of course, you could have biology on Mars. That's why those markers are the thing. And with James Webb, we will provide sensitive means to prove, map that quantity on Mars, if it's there. And I'm going to keep these two figures here for comment, and then of course the panelists, we can kind of answer questions about this. And so that's the main thing we wanted to showcase. I just want to say that we're all working the data. We are hoping that in the next few weeks, actually, we are trying to push, especially the 3.3 micron area, to see if we can tease that data to the high precision of the James Webb can deliver.
So, do we have questions from the room or online? Alex?
The visual, sorry, I was talking to the scientists here. The visual image we have of Mars is a small snapshot, the one on the top right. Will we ever get a sort of zoomed out image of the entirety of Mars from JUC, and why not?
That's a good point. So you see, we're using two filters here, and maybe the panelists can also expand on that. But the main thing is that because Mars is so bright, we cannot go deeper because if you use more pixels, then it saturates. So we had to use a narrow field of view, but it's a very high resolution so we picked the high resolution mode on Mars, but a narrow field of view. So anything shorter than 3 microns, it will be the stamp views, and for anything longer, it will be 4.3. The beauty is that Mars moves back and forth mass, and so it fluctuates in size. So you can play with the distance from Mars to make it Mars match in your field of view to make it fully complete and not fully complete. Again, these are very preliminary observations, but this is the time.
One from Zoom, two from Zoom, sorry. Alexandra Witz, Nature Magazine. What's the time frame for getting more information about methane?
Yes. Maybe you want to comment on, or?
Yeah, I think Geronimo already alluded to that. Methane is really tricky. So the current knowledge that we have about methane are really going in all directions, but all points to a very, very low abundance of methane, which means a very small feature, and certainly not as large as this simulation shows here, because here it's 50 ppb, and for the moment that's at least a factor 10 on the latest measurements. So you see that it means that we need to go to the details of all the spectra, calibration, reduce the noise, and that takes time. So, yeah.
We are actively working, so maybe Sarah, you want to talk about the data
if I can add, we're going to certainly work in the next weeks of nail down all the details of the spectrum, focusing on the 3 micron, 3.5 micron area. And of course, we're going to have to work very in detail for the systematics and understanding the spectra and the data themselves. So we'll see what we get. That's going to be work in progress right now. But yeah, that's our focus, of course.
Yeah. And I also want to highlight that, we have our team, which is the Mars team. But the video of James Webb, that is a full team of engineers have worked heavily on the calibration. So STSI is our main body, is in the US, who's working a lot on the calibration. So the idea is that also I was talking to other people from the Jupiter program, for example, we all learn tricks about how to process the data, how we improve the calibration. So we are working together in trying to develop a scheme that maximizes the data return. So, but soon this is our main priority. That's our main thing we're working on.
Yeah, exactly. We work together with the STSI team, of course.
And one more from Megan Bartels, space.com. Are these images available to download somewhere? And could you talk a bit about your plans for upcoming observations?
Yeah, so the images, I want to say the data, the raw data that we use for this analysis are publicly available already. They are on the master archive, so anybody can go there and just play with the data. And actually, this is a community effort, as everybody will said, so any indication coming from anybody would be precious to understand better the data. And as for new observations in the future, this was, as Geronimo said, a GTO, so a guaranteed time observation, meaning that it was programmed as as a one-time effort, but of course the community is free to, by learning how the data are processed, to submit new proposals for observations on Mars. Of course, this comes only in specific time windows, because Mars is available only in those windows there, but there will be occasions.
But that's exactly that. So the main thing is for the data to become publicly admitted is only for all of us to learn. We were a little bit intimidated how the process will be, so we learn about the data, and now we want to help the community to propose to new ideas. I'm pretty sure people will come very nice ideas how to maximize this instrument to pull new science. So these are the windows. There are multiple opportunities in the near future, and so this is just the beginning of what James Webb can do.
Do we have any questions from any audience?
The capability to observe 2.7 micron is really interesting in terms of searching for water on airless bodies. Have you ever thought about observing Phobos, or even more exotic, night side of the moon?
Yes, so that's a great question. Actually, let me show the image, because it goes exactly to this. So if you look at the 4.3 micron area, Mars is pretty bright. That's the challenge with Mars, and Phobos and Deimos are relatively close. And you have seen this very nice, beautiful of galaxies and stars, and there's all this pattern on the spikes of the mirror. So Mars being so bright produces a halo of what we call scattered light from the telescope around you. Being the moon so close means that you need to be able to tease out the Martian signatures very well when you look at the moon being so faint. But it's something that we want to aspire. And I think that actually we didn't plan it in the GTO program, in this particular program. We were focused on trying to get this, but it's something that I think some smart people will come with new ideas to develop observations that will be able to look at Phobos and Deimos. And again, back to the idea of James Webb that allows you to get the full spectrum at the incredible sensitivity. So I think there's potential for great science there too. Yeah.
What about night side of the moon?
Well, the challenge is that you see where we are. The moon is not accessible from us because of the field of regard. So we will not. It's going to be very difficult to do observations of the moon
Because of the Earth.
Because of the location. We have to avoid the sun, and the moon is on the back. So we cannot. If you want to look at the moon, you're going to be looking at the sun.
Do we have any more questions online? No? Any questions online? No? Okay, well, in that case, many thanks for sharing this with us today. The blog actually should be online.
Okay.
I'm not seeing it yet, but it should be online any moment, so you will be able to download the full images, the captions, and so on. If anybody here would like to talk to Geronimo or any of the other members of the team, then please contact us. So that goes for you online as well. And thank you very much for joining us here in Granada at the Europlanet Science Congress, and we hope to see you again on Wednesday for our second press briefing. Hopefully everything will run smoothly then. And thank you very much again. Thanks. Bye.